Well, welcome everybody. I am George Basile. I am the Associate Director for the Global KAITEKI Center here at ASU and also a professor in the School of Sustainability. We're very excited to have everybody here and to have our inaugural lecture for the Global KAITEKI Center. Professor Stratos, we were talking about this, Professor Stratos Pistikopoulos, you'll hear more about in a second. The Global KAITEKI Center is a partnership between ASU's Global Future Laboratories and the KAITEKI Institute, which is part of the Mitsubishi Chemical Holdings group over in Japan. And we really focus on bringing health and wellness and sustainability to society, with a great focus on circular economy and how we get there. And we're very excited to have Professor Pistikopoulos to talk about the circular economy in a sustainable engineering framework. Just a couple of housekeeping things, you guys. We're on a webinar here, so you'll look down, you'll see the Q&A section below. That's where you can enter questions at any time for the professor. And after his talk, we'll have about 15 minutes or so to go over and address those things. So with that, I'd like to welcome George Stephanopoulos, Professor George Stephanopoulos, who is the founding director of the Global KAITEKI Center, to introduce both himself and our guest speaker. So George, with that, over to you.
Good afternoon, everybody. I'm George Stephanopoulos, the director of the Global KAITEKI Center at ASU, and I am truly delighted to introduce today to you our special guest. Professor Stratos Pistikopoulos is the director of the Energy Institute at Texas A&M University and holds the Dow Chemical Chair in the R.T. McPherrin Department of Chemical Engineering. He has a PhD in chemical engineering from Carnegie Mellon. During his academic life, he has authored and co-authored over 500 major research publications, 15 books, and he has 4 patents in the areas of modeling, process control and optimization, energy systems, sustainability, circular economy, and systems engineering applications. He is a co-founder of Process Systems Enterprise, a very creative company in process systems engineering, which was so valuable that was recently acquired by Siemens. He is a fellow of the American Institute of Chemical Engineers and a fellow of the UK Institute of Chemical Engineers, and he is the current editor-in-chief of Computers and Chemical Engineering, which is the premier journal in computing in chemical engineering. He has received many honors and awards. I would like to note among them that in 2007, he was a co-recipient of the most prestigious MacRobert Award from the Royal Academy of Engineering in the UK. In 2013, he was elected Fellow of the Royal Academy of Engineering in the UK. And in 2017, he received the US Computing in Chemical Engineering Award of the American Institute of Chemical Engineers. And last year, he received the equivalent of the previous award in the UK. It is called the Sargent Medal from the Institute of Chemical Engineers. So at this point, without any further delay, here is Professor Pistikopoulos. The title of his lecture is Toward a Circular Economy Systems Engineering Framework. Stratos?
George, thank you. I hope everybody can hear me well. Well, it's an honor for me to be taking part at this very distinguished seminar series of the Global KAITEKI Center, led by Professor George Stephanopoulos, one of the most inspirational and influential academic leaders and thinkers of our modern era. And George has been a mentor and a role model for me throughout my academic career. So this has a special, place for me. So I would like to share with you some of my thoughts as we build towards what I will call a circular economy systems engineering framework. Before we start, I would like first to acknowledge the contributions of many bodies who have been working with us towards this, from NSF, the Shell, the Center for Water at Oaks, the various entities within Texas A&M. I will especially like to mention the School of Law and the Agricultural School that were collaborating a lot. And my special thanks, and a lot of the work I'm going to describe is due to my former PhD and current postdoc and the scientist at the Texas A&M Energy Institute, Dr. Siliana Avramidou. So just at a glance, my research group at the Texas A&M Energy Institute, and I would like to, I'm the spokesperson of the bright minds that work behind the, behind the scenes towards our research. And I could not resist the temptation to say a few words first about the Texas A&M Energy Institute, just to demonstrate the breadth and depth, it's one of the beacons of true interdisciplinarity within Texas A&M. And the current focus, if you wish, is to discover energy solutions which improve quality of life, breaking together what I will call, and that's a pillar for the thinking of the Energy Institute, this is systems-wide structure and approach in connecting technologies, both fossil and non-fossil, materials and agents which are important for the energy solutions of the future, together with the societal drivers, economics, law, policy, sustainability, and the glue that connects everything together, what we call the multi-scale energy systems engineering. That's the modeling, the data analysis, the medium that connects materials to technologies and link them to objectives, societal driven objectives. And we have a program that essentially looks at the landscape of the energy research, a strong program on education that I would like to touch upon in the next slide. And I would like just to highlight the truly interdisciplinarity nature, connecting more than close now to 300 faculty affiliates from all around the Texas A&M system, various campuses, and major state agencies involved. Just at a glance, one of the things that we're very proud at the Energy Institute is this master program that takes essentially, instead of a breadth depth kind of a depth-based type of look at the various energy aspects, it takes a breadth look at it, looking at the entire landscape of the various factors and key drivers in energy, so that we look, for instance, for energy law, materials for energy, energy technologies, economics and finance, resilience and sustainability, and energy digitization. And we have both in-person and remote program, both on certificate and matter of science, with the view to develop the next generation of leaders who look at the various aspects of the energy research and development landscape through quantitative analytical methods. And the model we have is more like an engagement model, like a partnership-based type of initiatives. We participate and lead on behalf of the Texas A&M space, or participate in major initiatives, nationwide initiatives like the US Manufacturing Institutes in rapid and smart manufacturing. This is led by ICHE, this is led by the UCLA, both are Department of Energy type of initiatives. We participate in the Superfund program. We have the master program. We have a long-term partnership with Shell and other organizations, and we're involved in a number of interdisciplinary activities across campus with various partners across the nation and across the globe. So let me go back to my to what I will try to do today is I will try a little bit to address the issues how circular economy, after defining, see the various aspects of it, how it is linked to much more formal systems analysis and what can engineering and science can offer. Then I will talk a little bit about some of the scientific needs and challenges, what in many ways pose us formidable tasks for the future, and then present a holistic approach, what I will name it as a circular economy systems engineering. So this is really a systems and engineering lens for addressing circular economy aspects. And that was the basis of a perspective article that we put forward recently, a year ago. And it was very much at the heart of the webinar that I gave a couple of months ago on behalf of the Sargent Metal prize that I received recently. So my favorite topic, for those of you who know me, is coffee. So I have been very privileged. One of the institutes and centers I collaborate a lot at Texas A&M is with the Coffee Institute of Research and Education. So, and for all of you who enjoy coffee, and this is like an espresso, it's an excellent motivating example, I think, because if you look at it carefully, just a cup of coffee uses 140 liters of water. I'll come back to this. I was very surprised when I saw this actually, and quite a bit of energy. And at the same time produces quite a significant amount, 5 times the amount of CO2 in weight, plastic waste, a lot of dry waste and spent waste, right? At the same time, one has to consider the economics of coffee, so this is after all is a product that we do not eat, it's inedible, yet, if you look carefully, and this is a 2016-17 type of figure, we're talking about only in the US, over $70 billion type of industry around coffee. So let's have a more closer glance at the supply chain of coffee. So, and why, all these metrics are relevant. First of all, coffee comes from a plantation. So you have nutrients that feed the coffee plantation. Then you produce coffee berries. Then those produce the beans. And at that stage is when you export and you package the coffee. You use plastic usually for packaging, and then taking coffee to the consumer through supermarkets. And this is the espresso that we all enjoy. So if we look carefully now, what is happening? First of all, the one thing to note is waste is created literally at every stage of the process. So at the plantation level, we have bad berries that never are processed any further. We have from the berries going to the coffee bean stage, we have a lot of coffee pulp, coffee husk, and the silver skim. So, so there is some separation from going to the berries to the beans. Then they might have also spillages and degradation when you try to go from beans to the package stage. You have plastic waste that's generated. You might have expiration, degradation, and all the stages all the way to the consumer. So that's one thing to keep in mind. The second important aspect, and that's where water comes into play, is that water is really used big time and contaminated at various stages of the process, especially for the plantation, then at the coffee beans level, and obviously when we actually make coffee. So that's the flow of water. The other dimension is clearly energy, and we need a lot of energy, and it's essential at every stage of the way, typically coming from fossil fuels, producing emissions, obviously. It's used for the plantation level, and you can see plays an important role all the way to the production of our beloved espresso and cappuccino. So, and that takes us to the question, what is circular economy and what has to do with the coffee? So if we look at the production from a coffee, from an espresso, looking backwards from an espresso production point of view, you can see that the production chain of coffee is clearly corresponding to the linear economy type of model. We'd like to produce coffee no matter what, and we'll produce a number of other things in the way. So what is then circular economy in that kind of arrangement is, first of all, to use as much as possible renewable type of energy source, substituting the fossil fuels. Then try to use reusable packaging as much as possible at the early stages for the packaged coffee and so forth. Collect waste and produce alternative products, so we don't essentially anything that previously was deemed to be a waste to be sort of a sink towards the production of alternative products. We'll come back to this later. And finally, try to return natural resources as much as possible to the source, clearly when it comes to water and nutrients in particular. So in that sense, we are abandoning, if you wish, the linearity of the classical model that has been prevailing, the production, supply, and value chain, towards the circular economy model, where effectively tries to not only minimize the resource extraction, minimize the landfill waste, and doing this by reusing, repairing, remaking, and recycling. So it introduces, if you wish, new pathways towards the introduction, looking at every waste as a source of potentially valuable new product line. But what is at least astonishing, and what we have found out, is that when it comes to definitions of what is a circular economy, there is a quite variety of at least 114 definitions. There was a relatively recent paper, conceptual, doing an analysis of 114 definitions. And you can see definitions of circular economy about maintaining products as long as possible, minimizing waste and resource use, low consumption energy and low emissions, the restorative and regenerative by design, nature, key materials and use, and so forth. So one of the theses of my presentation and one of the takeaway messages, we'll come back to this a little bit later, is that there is no consistent definition for circular economy, and there is desperately, especially we're trying to develop the science of circular economy, desperately there is a need of a scientific basis. Now, the key, of course, question is why bother? Why circular economy could become a driving force, both for science, for engineering, and for economic aspects and sustainability. First of all, is the important realization that most of the things we are dealing with, either a big proportion of this is wasted or is not used properly. And here is an example of this point, like almost 30% of the food is wasted. If you think about cars, we buy all these expensive cars, which only were used, 8% of their useful lifetime. And the service, car as a service, is gaining a lot of attention at the moment. Offices, we witnessed through the COVID, that, even before we were using only approximately 40 to 50% of the time the offices, now even less. So the whole concept of effective use of space is coming, is challenging, if you wish. And then if you look at one of the most important challenges of the modern era, like what are we going to do with the existing plastic that exists, and then how substitute, with biodegradable plastics, that opens up many new research dimensions. And then if you look carefully, and here is a slide that just reiterate the importance of looking at both at resources and waste. So here is the per capita, if you wish, tons and sort of annual growth of resources extraction in different categories, from metal ores, fossil energy carriers, biomass, non-metallic minerals. And you can see that we are over-exhausting our resources at quite a considerable annual rate. At the same time, the total waste generation and the waste generation per capita keeps on increasing, while the recycling and composting rate, it's around, in 2017 has been at the modest below, like around 36%. So there is a lot to be done towards this direction. If you look at it from an energy perspective, given that the world population is expected to go over 11 billion by 2100, and the energy consumption by a region is going to be increasing, especially due to the booming of the Asian countries and so forth. And given the importance of energy, which the energy is part of the growth of the GDP, so how we are dealing with the energy transition space in gradually introducing renewables to substitute in the scenarios of the future, and I will come back to this, in a sustainable and a circular economy perspective remains a key challenge for the modern era. So on the one hand, we have these rising populations which put huge stresses on the resources and on the natural resources. We have increased waste that have a negative impact on the environment. And then circular economy, especially if we approach it in a holistic manner, would definitely contribute to all dimensions of sustainable development in terms of economics, environmental, and social aspects. And perhaps it offers even a more consensus type of term towards a more politically and socially accepted term, avoiding, if you wish, debates about aspects like global warming and the rest. Obviously, circular economy now is gaining a lot of momentum, driven, and here you can see just a sample of various initiatives, both at the national level, at the EU level, also at company level, and very much mostly promoted by governments and businesses around the world, and somewhat, there is a lack of a systematic science-based approach to circular economy that offers tremendous possibilities for growth in the future. So, and that's the second, if you wish, key message that I would like to explore with you. So what are the links of circular economy to engineering and science and to systems analysis? Is it perpendicular to things we have been doing so far, or it is, we can borrow concepts and create a new scientific basis based on solid foundations? So if you look now carefully, at the various aspects now on utilizing resources extraction and producing, valuable products based on very valuable raw materials, that's where, if you wish, green chemistry and atom economy can play a very important role. Here is an example that on green chemistry, we don't need to go into the details, just to see that here is one route, if you wish, based on one particular chemical reaction that takes advantage of 81% of the atom economy. So that in terms, that relates to not so maximum resource, that you need more resource use to accomplish the same production level, where based on much more intelligent, clean type of chemistry, you can go all the way to 100% atom economy. So that minimizes resource use and minimizes as much as possible waste at the production stage. So green chemistry is a very important pillar towards circular economy. If you look at the food, energy, water nexus, where you look now at the interactions of energy, water, which is a natural resource, and food, which is an organic product in many ways, you clearly need a holistic approach to minimize the stresses between the nexus, the nexus, and it's a topic that I'll come into the moment. Process intensification is another way where you can guide the circular economy thinking, and it can be defined such as any process development that can lead to substantially smaller, cleaner, safer, and more efficient energy technologies. So for instance, here is an example, excellent, one of the textbook materials now where you have a very complicated, if you wish, process involving 11 plus units. We don't need to go into the detail. This is for the production of methyl acetate, where you can do the same thing in a single unit, and that can lead to over 70% reductions in cost, energy, and pollution. And that's, if you wish, the key, that has regained a lot of attention recently, and rapid stance. This is the Process Intensification Institute under the umbrella of DOE and AICHE. So, and it's an opportunity that the process industry is exploring, revisiting the concept of process intensification. If you look waste to products, reverse supply chains and industrial symbiosis, this is an excellent example where we can look at waste as a useful raw material for other type of interconnecting networks. So here is this is the concept where you use the waste heat recovery. So you use the excess of waste heat as a source for other parts of the production chain, cogeneration and byproduct exchange. And this is not, if you will, something that it's like an attempt, a futuristic attempt. This is happening at the moment. So there are examples where industrial symbiosis has really resulted in significant advantages in maximizing the benefits between energy flows, water flows, and materials flows. And then you have all the other aspects like life cycle analysis, supply chain optimization. And what I would like to, to connect, what is the connectivity of all those aspects, if you wish, and often different domain drivers, is that they can all be analyzed through systems and engineering and scientific type of approach. So let's look a little bit more closely now at some specific scientific needs and unique challenges that the circular economy may take us. The first important aspects that I think is quite challenging from a research coordination point of view is that you have interconnected, when you are dealing with circular economy, you have interconnected players. So you have multiple stakeholders, different domain experts, different pieces of legislation that may be applicable to different parts of the value chain, different policy aspects and so forth. And for instance, if you can look at it from a society point of view, the objectives might be totally different. There might be common economic sustainability and environmental, but obviously, the objectives and the means to implement those at different levels of the decision-making value chain differs. And you can see here that the connectivity between the societal drivers, the national and governmental bodies, and the network of industry and business. So this interconnectivity of different players with different objectives, different degrees of freedom, different pieces of implementation, and different stakes at any given time offer a unique challenge. The other important challenge, if you wish, is the inherent multi-scale character of the problem at hand, because you need to look, if you talk about atom economy, you need to look at the molecular level. If you look at the water, in the example of, let's say, of the food supply and so forth, you look at the plan and enterprise level. So you need to look in tandem at the various scales in terms of length and time. And you have also if you look at operation, we'll see later at the energy system, where you look at the electricity demand, obviously you have to look even at the level of minutes, even seconds, whereas the power generation happens at the level of hours and days. So this temporal and spatial system boundaries play a role. You have different data which come and different instances. So the data integration is an issue, model integration is an issue, and so forth. The other important challenge is that there is a huge uncertainty in the system. We're talking about reverse reaction pathways. There is variability in the system for demand, energy, solar and wind, and so forth. Costs, there are technologies that have not been developed fully, so cost is a variable as well. Resource availability, so there is a temporal also, there is a variability in space because you don't have all the sources at the same place, location, and time that you want. So all these aspects offer a very dynamic and uncertain environment that needs to be incorporated in such a holistic, if you wish, approach. And the final pillar, if you wish, of needs and challenges is the assessment criteria that you have on the one hand social, you have economic drivers, and you have environmental and sustainability, and you need somehow to synchronize this, to coordinate them towards with some global net sustainability type of metric. And the key takeaway and the thesis of my presentation that circular economy systems engineering offers such a holistic, systematic, if you wish, framework to bring together the various pieces of the puzzle together. So let me elaborate a little bit more on this through a number of examples which demonstrate different aspects of the circular economy systems engineering approach. So if you look from an energy transition first point of view, and we're trying to start substituting finite resources in energy based on a fossil fuel scenario towards renewable sources, then we can think about, for instance, taking advantage of wind and solar energy. So here is an example of such an approach where you're trying to optimize renewable energy carriers such as hydrogen, methanol, ammonia as part of a hydrogen economy of the future, where the production of these carriers are through mostly renewable type of technologies. And then you try to produce them where the wind is blowing and the sun is shining mostly, let's say in some parts of rural Texas, in the northwest in particular, and then ship this out and produce electricity a la carte for a particular percentage, let's say somewhere in New York. And this scenario that can be approximated or used in many instances around the globe. So, and this is part of a major activity that we have been working on at the Energy Institute for almost now 5-6 years in collaboration with the long-range research of Shell, where we're trying to transition for a reference case scenario based on primarily fossil fuels towards a scenario where everything is fully renewable, but there is no magic button that can take us from the reference case to the long-range aim. So the devil is always in the transition. So we're trying to analyze what is the optimal pathway through some hybrid transition period and technology case that can take us to the long-range aim, both in terms of time dimensions, in terms of technology dimensions, in terms of risk dimensions. So what are if you wish, some of the systems engineering aspects that are important here? So here is an example, for instance, of a map of the heat map of wind within Texas and the heat map of the solar intensity in Texas. And you can see that are the parts where you don't have neither wind nor solar everywhere. Whereas, and you can see that at places that you mostly need, you are not blessed to have not as much wind and as much solar as some other parts which are not as populated. So the idea here of the approach that, so in order to address this important challenge, you bring together aspects of detailed design, if you wish, on the production of these chemicals, taking into advantage how you are going to design the supply chain that will bring those chemicals to the market where you need it, and delivering, if you wish, electricity through, through some installation of some battery capacity, also with the wind and so forth, so that you synchronize the operation on the electricity demand based on the supply chain and the production. And what you're doing here, in essence, from a methodological point of view, you're trying to address the various multi-scale issues. Here we have multi-scale issues in terms of time, because there is not synchronicity between the production of electricity, which is, let's say, the minute, or like the delivery of electricity at the millisecond, if you wish, time scale with the production side and the supply chain, as well as in terms of dispersity, in terms of where the sources are, in terms of actual location. And then you bring together various components of methodological aspects, like the fact that you need to trade, if you wish, energy efficiency versus life cycle analysis metrics versus type of risk in terms of technology, given the uncertainty and the stochasticity that exists, and you bring together modeling through data, design aspects, and operation. And that is one example of one particular system, like of an energy, the design of an energy system for the future. Now, if you try to bring in tandem with such a holistic approach aspects related, for instance, to water and food, things are getting even more complicated. So let's have a glance as an example on the food, energy, water nexus. Here is a project that we have been involved for the last few years, just as an example to see the key messages here. So we're looking at San Antonio. It's a regional L in Texas. And this is pretty much the metropolitan area of San Antonio. And what I would like to draw your attention is the various colors. So you see, this is the various, if you wish, dots where water is used: blue for municipal, green for irrigation, and red for energy. And now what is important here is not only that, these are competing with each other, as the population is growing and the precipitation keeps on going down. So there is a demand increase in terms of water, competition between municipal, irrigation, and energy. But what is even more striking is that different pieces of legislation, if you wish, guide the operation and the whole market of how water is drawn, for instance, by the city, by the agriculture, and by the thirst for the wells that are scattered around the region. So here you have a classical example of interconnected players, which have different stakeholders that are governed with different policies and laws, and they have different objectives, and they coordinate different parts of the nexus, if you will. So you have government, you have business, you have society, and you can see that there are different ways that these stakeholders interact with each other, and addressing these nexus hotspots in a variety of ways. And the key point here is that there is no a unified, if you wish, legislation and policy protocol that governs these interconnected players. And that's very important. And it's the first time, actually, last year, a couple of years ago, in 2019, that we saw this integration of energy and water research. So this that passed through the bill passed through the House Science, Space and Technology on the subcommittee on energy. And here is, I would like to draw your attention that to ensure consideration of water intensity in the Department of Energy's energy research development demonstration programs to help guarantee efficient, reliable, and sustainable delivery of energy and clean water resources. So the time is coming for even legislation and laws and policies to follow the need for such an integration that essentially will allow us then to start addressing the complex systems and networks that underpin, if you wish, the links between the important research questions and business objectives and practical aspects as we try to navigate the space from a municipal point of view, from an agricultural point of view, from a water point of view, and from an energy point of view. So just if you take, if you wish, as an example, the energy in red shown here, key question from the energy sector to the municipal sector is what is municipal energy demand? What is a profile for the future, and how we can do what will be the optimal energy portfolio mix, if you wish, to meet this municipal demand. From a water point of view, what is the energy footprint for water? What is the optimal portfolio to meet water demand for energy? And then what is the energy footprint for agriculture, and so forth and so on. So we can understand now the interactions of the various aspects of the extended, if you wish, value and supply chain. So that offers huge challenges, both from a methodological, but also from a policy aspects, as well as creating the necessary legal frameworks that dictate, if you wish, the design and operation of such systems. And that takes us back to my favorite topic, which I hope you have fully comprehended by now, which is coffee. So let's revisit now the supply chain of coffee and look at it like from the point of view on how we create a holistic framework towards analyzing, designing, and creating opportunities for the future. So question number one is, how can we make informed decisions for the transition from a linear to a circular food supply chain in general? And let's use coffee as an example. So this is some of the key pillars of steps, if you wish, towards what we call a systems engineering framework for the analysis and design of the circular economy systems of the future. And I'm looking, so we're looking at production pathways, waste utilization pathways, a representation that includes these alternative pathways in a cohesive type of mathematical model that then we analyze and solve, and then analyzes from a risk, cost, energy efficient, and the like. So just to give you a flavor of what this methodological framework is all about, here you see a number of alternative production pathways from fresh coffee cherries, different methods that exist and different steps for every method. Then you can have pathways as far as waste utilization is concerned at the pulp, husk, silver skin, and spent coffee ground, so those open up even more possibilities. And then if you put everything together, this is like a reverse supply chain, if you wish, creating a biorefinery, mimicking a biorefinery, if you wish, based on spent coffee grounds, right? So we can start now analyze. So that's where you need to be an understanding, the pathways, the chemistry involved here, the production facilities, does it make sense from a life cycle analysis, from a cost point of view, and so forth. And here is some of, initial results of what this type of analysis can do. This is like, if you wish, a representation that allows you to put all those conceptual pathways together, and then you can do like some type of modeling and optimization to come up, for instance, with promising pathways. And then you can do trade-off analysis, like trading off energy versus minimum waste, and see the various scenarios in terms of different production steps, if you wish, based on these various options that we are heading. and that gives you with some means to be able to assess this type of scenarios in a systematic way. And that brings me to the final points that I would like to make in this presentation. First of all, the desperate need for a unified metric. And here what I'm trying to attempt is like a glance of a first attempt towards such a metric development and for, let's say, for the use of various businesses, industries, and so forth, where you look at reduction of material losses through the waste, reduction of input and use of natural resources of procurement and water, increase in the share of renewable resources, that's the energy, if you wish, dimension, emissions and spillages, and then durability, let's say, that links to resilience and reliability. And just as an example, like energy, you're trying to measure what is the percentage of the penetration of renewable energy vis-a-vis the total energy consumption that an organization, a company, or a business needs. And that allows you to start now creating maps of solutions and visualization tools like this, where you can map the waste, the emissions, the energy, the water procurement, the durability in terms of an index as a function of time, or from 0 to 1. And then you can see, for instance, how you trend in terms of durability, in terms of water, and the rooms for improvement in each one of those vectors. And you can go even a step further and aggregate all this, let's say, by taking like a combination of all these metrics in some scientifically sound way. And you create, let's say, an index for circular economy, which gives you your overall performance as a function of time. And that can be used as a valuable information, both to consumers, to producers, to businesses, and to the market as a whole. So let me close my seminar by first looking at some open research questions, which I hope are articulated through the exams and the various challenges. First of all, I think one of the key aspects is an attempt to develop some kind of a consistent basis so that we are able to compare different alternatives towards circular economy on an apple-to-apple basis and not on an apple-to-orange basis. Then a second major open question is the uniqueness. There are many combinations. I highlight some of these that you can arrive at circular economies. Which ones are scientifically, analyze them from a thermodynamic limit point of view, analyze them from a uniqueness point of view, robustness, resilience. So which of those are going to be more efficient from a techno-economic point of view, but also, from an overall point of view, from a life cycle point of view. Then it's the issue of scale. Are we talking about, is it better to go towards centralized type of systems design or decentralized? In other words, is it more suitable to think of a system for a circular economy based on decentralized aspects or not? Policy regulations play pivotal importance, not only in providing, if you wish, incentives towards the adaptation of circular economy, but also because they play a key role, if you wish, in the acceptance of such approaches. And then, of course, the overarching, if you wish, challenge remains we need desperately a science-based engineering with different systems and approach along the lines that I have been offering. So a couple of takeaway messages to close this seminar. Circular economy relies on systems-wide innovation. So it has been primarily led by practitioners, the business community, and policy makers, and there is a need for building a strong scientific basis. I have articulated the fact that a systems engineering approach can have a big impact on the understanding and analysis of building circular economy supply chains and towards the convergence of different disciplines towards a common vision of the subject. So I articulated that a circular economy systems engineering provides the glue between various domain and science and engineering basis and links to policy, regulation, and sustainability approaches. And finally, I would like to close that it can offer also a model for the generation next, if you wish, from a societal point of view, bringing science-based systems analysis towards materials, effective resource utilization, health aspects, the nexus, which is going to be a pivotal challenge for the future, and overall sustainable manufacturing. Thank you very much. I'll stop at this point. I will be glad to take any questions. And let me iterate how honored I am to be the part of this distinguished seminar series here at the Global KAITEKI Center at Arizona State University. Thank you very much for your attention.
Stratos, thank you. Thank you very much for a wonderful lecture. We just have really a few minutes of time, everybody, for some Q&A. And let me start off with one question, and we'll get to some of the ones that Stratos, that was a really, I think, comprehensive, holistic approach. And a number of times you brought up this having to balance where we are today with tomorrow, this notion of transition. And I think that folks in engineering and in chemicals and processing and systems analysis often have a lot of confidence in optimizations that folks in the sustainability field don't necessarily share. So I wonder if you could talk a little bit, and maybe this is within the Texas energy crisis and the Shell example, optimization versus sort of adaptive management, how the systems approaching you're bringing actually lets us be flexible and adaptive.
Yeah, that's a great point, George. Thanks for bringing, there is an opportunity for convergence of terminology and expertise, if you wish. And in my opinion, I can see convergence between, an adaptive type of management, which essentially tries to navigate the transitions from A to B to C in an adaptive manner through modeling and this type of systems approach, which essentially can mimic, so we can create, if you wish, modeling paradigms which can converge the adaptive management style into some quantitative kind of analysis. So I see this as an opportunity for convergence of the various fields. And especially for navigating the transition space, and I see there was a question on how, do we exclude, what do we include in the analysis of transitions, or do we exclude many aspects? I think the wonderful thing, and why I passionately believe in circular economy as a model, and I offer this holistic approach, is that we don't exclude anything, in fact, because if you look at, if we find a technology breakthrough that can take us back to the natural resources, be it fossil or whatever, that in a way essentially addresses, the balance of renewables versus any other type of scenario, right? And this is especially intensified by the fact that there is not a magic button that can take us, as I said, from A to Z. And if you think also, many people advocate the use of batteries as a solution to everything, right? In the scenarios of the future. And that's another exercise or an adventure really in resources utilization, and if you look at it from a life cycle analysis and resources utilization in general, where are you going to find the lithium or any other rare metal other than Bolivia or any other country, right? So essentially, one of my key takeaway messages, and I think what the community as a whole, as a scientific discipline is converging, is that everything is on the table, and that we need, and that's my thesis on top of this, is that we need a quantitative framework that will take us through the most promising, perhaps, solution spaces, and that will allow us to navigate in a consistent basis. So when we compare various scenarios, we do this in a holistic means in a multi-attribute point of view, bringing the various stakeholders together, and in systematic way. So that's the key message.
Yeah, and that's interesting. We have another question from Kevin Dooley, a professor here in the business school and who works with us at the Global KAITEKI Center, noting that a lot, and I think this is important for what you're saying, externalities, the current externalities are often only come into the conversation at scale when we see the economic implications or through some sort of policy push. Just given what you've described and through your talk, it sounds like you feel like doing by bringing visibility to these pathways and to these externalities and how they aren't just negatives, but they're pathway models, they're ways to solutions. We can maybe open up another leg in moving to action rather than just economics or just policy and through knowledge and visibility? Or do you still feel like, yeah, no, at the end of the day, it's economics and policy and we're just bringing the science into those two big buckets?
I think you need two to tango, sometimes three, right? So in a way, policy definitely can drive science. Technology can offer pathways towards new possibilities, but at the end of the day, we need to synchronize the business drivers with the policy drivers and the technology drivers, right? Now the dynamics of these spaces may be different. You saw the example, the food, energy, water nexus. Some of the science exists almost for a decade or so. Only recently there was a need to, from a legislation point of view, to synchronize water with energy, right? So we need to pay a little bit more attention on the time constants, if you wish, of the system towards reaching solutions that can deliver such holistic approaches. Clearly, the business driver often, cannot be overlooked for sure, but policy can offer incentives and technology solutions, by bringing different science domains and an engineering approach to things is necessary to provide the glue towards what can happen and what cannot happen.
Right, absolutely, and it can create trust.
Exactly. The risk, understanding of the risks involved, not only in terms of cost, but technology, but also confidence, from an overall, acceptability point of view.
Well, unfortunately we're out of time here. We have another, one of our guests said maybe we should talk about the conical economy as we add another dimension of consumption. And then one of my colleagues internationally asked about the speed of change in technology. So you guys, we'll have to leave everybody with.
We are bound by the speed that we need to go within an hour, but speed of change is attached upon it because that's a risk, right? So, when you do this analysis, the time dimension, like acceptability or readability of the technologies and acceptability by solution at different time instances is very important. So
yeah. All right, let me thank you again, Stratos, but let me turn it over to George Stephanopoulos to close us out here.
Stratos, can you hear me?
Yes, George.
Congratulations. This was a wonderful tour de force on the system science behind the circular economy. We take your message very, very seriously, and we agree with the main thrust of it. Your overall comprehensive and integrated view is, as in our opinion as well, the way forward. And as the Global KAITEKI Center, we look forward to enhance the interaction with you as time goes by. One thing that I did not mention is that this webinar comes with a compulsory physical visit by you to ASU. And I know you are vaccinated, so we will be discussing how we can do that at the earliest possible.
We'll be delighted, George. Thank you for the kind invitation.
Whoops, we lost George there for a second.
The time our gratitude for this special event to present to you. Can you hear the like?
You're cutting in and out a little bit, George. So
The image?
there you go. You're back.
Can
All right.
you-
Oh my
can
God.
you say
Oh my God.
like we prepared?
I'm very honored. I would like to thank you all. I mean, it's a great honor.
Distinguished KAITEKI Lecture is presented to Professor Stratos Pistikopoulos.
Thank you very much. I mean, this is a great honor. I would like to thank you all.
For your mentions in theory and applications and sustainability and your inauguration.
Thank you.
You're going to receive that in the mail.
That's great. Thank you so much.
All right, let me jump here. Thank everybody who's still here. Stratos, a real pleasure, a real honor. We'll of course follow up. And anybody who's still out there, we're happy to gather questions and share them with Stratos. And congratulations on being our first distinguished and inaugural lecturer. And with that,
the honor is mine. Thank you all for attending. Great.
All right. Cheers, everybody.
Bye-bye.
Bye. Thanks all.
Bye-bye.